Okay, the purpose of this podcast is to demonstrate how to find the distance of a plane from the origin using the Cartesian form of the equation of a plane, and also to demonstrate why it is that the particular expression used to find the distance works, how and why it is that it works. And so what we're going to do is work with an equation of a plane in Cartesian form, and that particular equation for this example will be 10x plus 10y plus z equals 109. In this particular case, in order to evaluate the distance of this plane from the origin, all we need to do is use the expression d over the magnitude of n. In this particular case, the d value is the value on the right hand side, 109, and our normal in this case is 10, 10, 1, the coefficients of the x, y, and z variables. And so in order to evaluate the distance, we simply take 109 and divide that by the magnitude of the normal. And in this particular case, therefore, our distance of the plane from the origin would be 109 divided by the square root of 201, which would be 10 squared plus 10 squared plus 1 squared, and that yields the distance. That's all you need in terms of finding a distance. The remainder of the podcast will focus on why it is that this particular expression yields this expression over here, why it is that this yields the plane's distance from the origin. And so what we're going to do, just for some visual aid, is plot our plane, and I'm going to add the equation over here. The equation is 10x plus 10y plus z equals 109, and we see a representation of that plane on the graph. And what we're going to do at this point is attempt to show where the right triangle appears in this. What we're attempting to do is to show the distance of our plane, or represent the distance of our plane from the origin. And so the first thing I'll do is just add a point, and the point that I'm going to add is the point 0, 0, 0, which is the origin. The second thing that I'm going to do is I'm going to have an equation of a line, and the equation of the line is going to pass through the origin and be perpendicular to the plane. And so the way I'm going to ensure that it passes through the origin is, of course, to use the coordinates of the position vector 0, 0, 0. In order to ensure that it's perpendicular to the plane, I will simply use the parameters of the normal, or sorry, not the parameters, the values of the normal for the slope of the line, or the direction vector of the line. And in this particular case, we have the following. And what I'm going to do, just to make it hopefully fairly clear, is show an XY orientation of that. And hopefully what becomes relatively clear, or what should be fairly obvious, is the triangular shape that is created with our normal passing through the origin. And what we're going to do now is go back to the notebook and I'll be using the triangle to demonstrate why it is that the d over magnitude of n yields the distance that we are after. Okay, and so to begin with, what we're going to do is just modify briefly our diagram. And what we're going to do to begin with is take a look at that over there, and the object of highlighting that is to show that what we're attempting to do is have this represent a side view of our plane. Okay, over here we're going to have theta. We are treating the O as the origin. This point over here I will call point T, and this point over here I will call point R. The idea would be that R would represent a point on the plane, as would T, but we are going to use point R because it does not have the characteristic that it is joined from the origin to the plane at 90 degrees. And so it's meant to represent any of the points on the plane, and hopefully it's clear on the left hand side that that point would be approximately where I'm showing on the graph. Okay, and what we're going to do now as well is I'm just going to highlight one other thing. I'm going to draw another line, or rather another vector, and I'm going to treat this, even though by definition it is a position vector, I am effectively treating it as a vector, and I'm going to label my vectors from O to T. In order to get from O to T, we would be using the direction of the normal. If this is our plane, then the normal, of course, intersects the plane at 90 degrees, and the evaluating of distances between points and planes, and the origin, of course, is a point. By definition, we always use the shortest distance, which occurs at 90 degrees. Okay, OR I'm going to treat as a vector. Even though it is a position vector, the coordinates of R, whatever they happen to be, if I expressed OR instead as a vector, which I'll call vector A, it would be R's coordinates minus the origin's coordinates, which would simply yield R's coordinates. Okay, and what we're going to do now is just give a little bit of extra space. Okay, and so to begin with, what we're going to do is use very basic right triangle trigonometry in order to find an expression for OT. OT, of course, being the distance of the plane from the origin. And so OT would equal magnitude of vector A, and in this context this is of course our hypotenuse opposite the right angle multiplied by cos theta, and all we've done is used right triangle trig SOHCAHTOA, and we've used cosine is equal to adjacent over hypotenuse and rearrange the expression. The next thing we're going to do is relate this to the angle formula in vectors, and that formula of course is cos theta is equal to the dot product of the two vectors. In this particular case, I'm going to, in order to be consistent with the diagram, use excuse me, dot product of A and N, because theta is the angle between the vectors A and N, and that would be divided by magnitude A multiplied by magnitude N. I'm going to rearrange this equation by multiplying by both sides of the expression by the magnitude of A, and I would then have magnitude A cos theta on the left hand side. I would have on the right hand side dot product of A and N divided by the magnitude of N. And it hopefully is fairly obvious that the magnitude of A times cos theta also equals OT, OT being the distance of the plane from the origin, and so this gives us the value OT. And really the last piece to understand or to recall in terms of Cartesian equation of a plane, recall that the Cartesian equation of the plane in vector form, or sorry, an expression for the Cartesian equation of the plane is the r dot n equal to a dot n. A, of course, represents a position vector or a point on the plane. N is the normal, and r is our general point in the plane x, y, and z. And again, in general terms, the normal is represented with the components a, b, and c. In general terms, our position vector is represented as xo, yo, and zo, and we also should recall that a dot n is where we obtain the scalar value d, and again, as we can see from our equation above, that our normal is 10, 10, 1. The d value, the scalar, which would have been obtained from the dot product of the normal and any point within this plane, produced a scalar value of 109, and hopefully now it is clear that the dot product of a and n, which is in fact d, divided by the magnitude of n, yields the size OT, or the magnitude or length of OT, and that in turn is the distance of the plane from the origin.